Back again to that phrase, a computer program is a list of instructions we write in a programming language the computer understands. I said this sentence was useful, but not entirely true, and it's this bit. The programming language the computer understands. Well, because the computer does not understand our source code. We will use a language like C# or Swift or Ruby or Python, but the chip, the central processing unit or CPU in any computer, laptop, desktop, phone, server, game console, this is the piece of hardware that takes care of running or executing our program, and it doesn't understand our source code at all. The only thing this understands is what's called machine code or machine language, which looks like this. And these are the basic instructions like add one number to another number, but now written in a form the computer understands. Now, if looking at this makes your eyes glaze over, that's totally okay. That is an appropriate response. This looks like gibberish. It's intended for machines, not humans, and you do not need to be able to read this. The vast majority of professional programmers never ever deal with machine code. Now, it is possible to write a program in machine code. There are a handful of specialized positions where it's a skill, but it's not a general programming skill. Writing machine code is incredibly time-consuming. It's a long, error-prone, painstaking, and tedious process. Not only that, machine code is slightly different across every version of every chip, across different hardware. The entire point of having programming languages is so we don't have to write machine code. But if we only write source code and the chip only understands machine code, then that would suggest our source code must be converted into machine code before the program can run. And yes, that must happen. There's two main ways to do it. We will either compile or we will interpret the source code. And the difference between compiling and interpreting is not about what happens, but about when does that conversion to machine code happen. Here's what I mean. Imagine I've written a simple program. So I've written some source code on my computer, and I want you to run my new program over on your computer. I've written source code, but your computer needs machine code. Option number 1, compilation. I will take care of this. I will use a compiler. A compiler is a program that goes through my source code file instruction by instruction and converts it into machine code. The compiler spits out a new file containing machine code, so that's something your CPU can actually now understand and run or execute. The result of the compilation is called an executable or executable file. After I've compiled it, I just give you that new file and you can run my program. So when compiling, you won't get my source code. It stays on my machine. You don't even know what programming language I used. Option number 2 is we use an interpreter. Now for this, I still have my source code, but instead of me compiling it, I just give you a copy of it. You get my source code, and that means you need to do the conversion to machine code, and you will use an interpreter to do it. Now that doesn't mean you have to go out and download an interpreter program. You will often find interpreters are bundled inside web browsers or even operating systems themselves, and they will be used automatically. Probably the most common example of an interpreter is that there is a JavaScript interpreter inside every web browser. So if I just sent you some JavaScript, you can run it because your browser knows how to interpret it. Now, one big difference is that with an interpreter, this conversion to machine code doesn't happen in advance. It doesn't happen until you decide to run the program on your computer. And at that time, the interpreter goes through that source code instructions line by line and converts them to machine code instructions as needed, then runs that machine code. It doesn't save it as a separate file. Now, there are genuine benefits and downsides to both methods. Compiled languages can often create faster programs because you've done the conversion in advance. But one downside is that because machine code is platform specific, if you compile your program so it runs on a PC, that means it won't work on a Mac and vice versa. Some languages support compiling multiple different versions of your program for different operating systems. Now with interpreted languages, they're often cross-platform because as long as the person you're sending your source code to has the interpreter, you don't care what operating system they use. But interpreted programs can run slower because the conversion still has to happen in addition to running the program. And on top of that, with interpreted languages, you also have to give your source code to whoever wants to run your program. That could be both a benefit or a hazard. Now, it is true there is a third option, somewhere in the middle of this. Modern languages often try to compromise by having programs that can be partially compiled into an intermediate state, an in-between state, what's often called intermediate language. Another term is bytecode. It's a way that you can do as much of the compilation as possible in advance, but not quite all the way to that platform-specific machine code, leaving the final step, what's often called just-in-time compilation, is done on the computer of whoever is running the program. Now, all of these options are important to know, but it isn't something you need to worry that much about or even have to make a decision on, because most programming languages naturally fall into either compiled or interpreted or in-between categories. There are always edge cases and exceptions, but a handful of examples here of what's most common. For compiled languages, C++, Swift, C, Objective-C, these are typically just compiled. JavaScript, Python, and PHP, these are typically interpreted languages, and the best known language that takes that middle ground hybrid intermediate approach is Java. But you won't choose a language just for its compilation model. You will decide on the language for other reasons, like what platform or what type of application are you making. And then you'll need to understand the way that source code in that language actually makes it onto the CPU. Having covered that, it's about time we dive a little deeper into some specific source code.